Today's talk is presented by Kateryna Hlyniana and devoted to filtration problem for stochastic differential equation with interaction. Please, Katya.
Okay, so today I will present some results of joint work with Professor Andrei Dorogovtsev and our colleagues from university. So we started the filtration problem for stochastic differential equations with this interaction, and we started to get some results. So I want to present them to you. So first of all, I recall what is the equation with interaction that we considering. So since we worked with it on this seminar quite often, I will briefly recall that we have the equation in which in the right hand side the coefficients depends on the mass distributions mu t, which is the shift of measure mu 0 by all flow x. So here on the right hand side, I write the coefficient not in the winner sheet, but using the an independent standard winner processes just for simplicity, for formulas that we will get. And even sometimes I need this summation and write just product B times dw, but we can easily rewrite all results for sum of n summands with independent winner processes. So since we are considering a filtering problem, we interpret the solution to this equation as a signal. So this is what we want to know. And we will consider not the process X, the whole flow, as a signal process, but we will consider a measure valued solution to this equation. So here I write that we will consider the process mu t as a signal process. I'm sorry. Okay, and as usual in filtration problem, we cannot observe a signal process itself, but we observe some functional of signal. So we will consider the following functional. So this will be an integral from 0 to t from some function of a measure, and plus some noise which is independent with winner processes here. So this is what we have, and now the problem is to get the conditional distribution of the measure mu t given information of observable process y. So I will now give more precise definition. What does it mean, the distribution of a measure? So we need to work, we need to fix we need to fix a space where we will consider the distribution. And for this, I recall also 2 seminars ago, Alexander presented Wasserstein space of probability measures. So I just recall that I will consider the space of probability measures with second moments, that is mu probability measures, and such interval is finite, and the distance between two measures is defined as follows. So here we take infimum over integrals of such integrals. So here the distance between 2 points with integration over measure rho, which has marginal measures mu1 and mu2 correspondingly. So I will not stop here because we saw this definition before. But having this distance and this space, now we can give a condition under which the solution to the stochastic differential equation exists. So this is the results of Andrei Anatolyevich Darogosov. So the coefficients of equation should satisfy following Lipschitz condition. So the Lipschitz condition, the Lipschitz continuous with respect to space variable and with respect to measure valued variable. So here we use this distance gamma 2 of between measures with a second moment. And the statement says also that if we start from a measure which has a second moment, then the solution, so mu2, will be also an element of space of probability measures with second moments. Okay, so now I will suppose that we have these assumptions for coefficients A and B. And what is the problem that we want to solve? So now when we have a distance on the space of measures, we can consider Borel sigma algebra on space of probability measures. And it is known that this space is complete and separable. So under this, so with these properties, we can guarantee that the existence of regular conditional probability distribution of random element in this space given some sigma algebra. So now we can define what we want to find. So we want to find this regular conditional probability distribution of measure mu t, given sigma algebra of observable process. And as usual, we call this measure valued process P, an optimal filter of mu t. So here, I want to say once more that PT is a measure on space of measures with second moment. Okay, so but Usually it's not easy to find the probability distribution itself. So people find not the distribution of measure μt, but the conditional expectation of functions from measure given the sigma algebra yt. So here, if we consider quite big family of functionals f, then we will know everything about the distribution p itself. And just as a small remark, which is known, that the conditional expectation will give us the best estimate for functional of measure μt in mean square mean, and so that's why we understand this conditional expectation as a estimation of signal process given observable process y. And the goal for us is to find the equation for this conditional expectation. So we have a process which is indexed by time t. So we expect to find the stochastic differential equation for this process for some class of functions on space of probability measures P2. And before I will present what we can do in general case, I want to show an example just to understand what kind of problems and how we can reduce them to known results of in filtering theory. So let us consider the following linear equation with interaction, in which motion of particle depends on the position of the center of mass of the system. So this equation is given as by the following. This motion is described by the following equation. Here we have just one linear process for simplicity, and the right-hand side, the coefficient in right-hand side is depends on center of mass mt, which is calculated by this formula. So here we just have the integral of measure μt. And the solution to this equation has the following form. And maybe let us see how we can get it. So it's not hard to see. And for this, we write the equation in integral form. And when we have this equation in integral form, we can integrate the right-hand side and left-hand side with respect to initial measure μ0. And so in right-hand side, we will have center of mass of system at time t. And on the left-hand side, well, everything will be rewritten in terms of like here, when we integrate the second term, it will disappear at all, because we will have here just center of mass at time s minus center of mass at time s itself. so it's equal to 0, and the integral with respect to Wiener process. So here, this is a simple case, and the noise doesn't depend on space. So integration with respect to U just disappears, and we have the equation on the center of mass. So we can see that mass just moves, the center of mass moves like a Wiener process itself. And now if we subtract, so we can write the differential equation for centered system x minus center of mass, and from this here we can see that this equation deterministic, and we have the solution of the following form. And for simplicity, now let us assume that center of mass, that initial center of mass is located at 0, and then the solution is simplified as follows. So we have the stochastic part, which is just Wiener process, and this just from the solution to the linear deterministic equation. So now when we have this solution, let us come back to filtering problem. So let us assume that the observable process has the form, in the general case, I wrote here some function from measure. So let us take this function equal to integration of some function f with respect to measure mu s. So now this functional just written as follows, and here now we know the solution x, so we can substitute it here. And that I do here. Well, for now, to get the result for filtering problem, let us consider more simple case when this function f is linear. So this means that we observe just so-called average of signal process plus some noise. Of course, here we have a constant. So when we have this solution and f is linear, recall that initial center mass is equal to 0. So when you integrate u with respect to mu 0, you will have 0. And here, integrating w, we just have the average of, not average, just integral of a Wiener process plus independent Wiener process. So now, as we see, if we want to find the conditional expectation, or if we want to find, so we want to find the conditional expectation of such functional of the measure mu t, and here again, if we substitute the solution, we can see that it depends just on Wiener process itself. So that's for finding the conditional expectation, we just need to know the conditional distribution of Gaussian process with condition on another sigma algebra of Gaussian processes. So in this case, for linear observable process, the measure valued problem or in filtering problem reduced to just known conditional distributions of Gaussian processes. So this is what one can get in this case. Okay, so now let us come back to general case and
Excuse me, could you please show us one more time previous, and why beta disappears?
so here when we consider so this is Gaussian process, and when we will calculate the expectation and variance of W with respect to not some but one Gaussian, the sigma algebra generated by this Gaussian process and this Gaussian process, since W independent of beta, you will get that the expectation and variance actually doesn't depend that, because we have that covariance is equal to 0. So the answer, you will not get that the dependence of beta.
Yes, I'm sorry, but it should be like a function of what stands in the right hand side. So beta should still be used to formulate distribution.
So if I consider first
maybe you need to integrate with distribution of beta, the result.
You see, your result is a function of the right hand side.
Yes.
But these two functions, the second function is not a function of. This function is fundamentally different.
Maybe no. Yeah. So is it true that integral from 0 to r ws ds is a function of the sum? Integral plus beta.
Maybe yes. Maybe it's not true.
This integral. So W and beta are independent. So when we will consider just the condition on two Gaussian processes, this integral.
So
and
you see the result, for example, you have to calculate probability that one Gaussian random variable belongs to delta given xi and zeta.
Right. And
this result is some function of xi plus zeta. But this function is some function only of xi.
Excuse me, here we have some misunderstanding. Of course, if we have sigma field which is generated by W and beta, comma beta, then this formula is right. If we have a sum, then of course this formula is not right. So we need to add something. Yeah? But maybe we can just think now that here is comma not plus, then the result is okay. Yeah.
But we still can calculate like the conditional distribution.
Surely it can be calculated. Yeah.
I see.
Okay. I will move next. So as we can see, I said in the previous slides, we will consider observable process of the following form. So here we will integrate some functional of measure, and we suppose that f is bounded real valued function. For example, as we considered in example, sometimes it's easier to understand how to get formulas, just to consider example of such integral with respect to mu s, or the integral with respect to power of mu s. So this is just how we can understand the functionals of observable process. And here I will use the approach which is well known in the filtering problem. So in order to find the equation for conditional expectation, we will use a change of measure approach for so why do we need it? So let me give you some explanation. So we will change the measure initial probability measure such that y will become just a Wiener process itself, which will be independent on x of I'm sorry, of mu. So how to do it? So when we have shifted Wiener process, we know that Wiener process is the distribution of Wiener process is absolutely continuous of with respect to the distribution of shifted Wiener process under some assumptions. So if we define a martingale of the following form, so here why I call it martingale, because I assume that f is bounded. So here I just for simplicity show the case when functional is just integral with respect to measure mu s. So here everything we assume bounded, and so this process is a martingale, and we defined a measure p hat such that it has a Radon-Nikodym derivative which is equal to this mt. And sometimes I put here tilde, sometimes hat. I'm sorry, this is the same. So then with such new probability measure p tilde, the observation process y will be a Brownian motion, and it will be independent on functionals of mu t for any continuous maybe I should here write bounded function on space of probability measures. And additionally, the law of signal process, or like I will write the function of mu t under p tilde will be the same as its law under p. So to see this, actually the first part which says that y is a Brownian motion is just a simple application of Kirsanov theorem. But to see the second part, which says that now mu t will be independent of process y itself. So if I consider just a function of measure mu, then this the law of pair processes can be written like this. So here we have two coordinates, and the second coordinate we shift. So then the distribution of this pair on the interval 0t will be absolutely continuous with respect to law of shifted processes. And
what is h? Is it just
h just some function of bounded function of measure, just to somehow to work with, not to work with measure.
So it is real valued
yes, real valued function. So just here to work with not with measure valued processes, but with this real valued processes.
And yt is the observable.
Yt is observable process, right?
Okay, thank you.
And why do we have absolute continuity? We have absolute continuity for the second coordinates.
Yes, and the first is the same. So we have like if we will write the distribution of this
it seems
pair.
to me that the general fact is incorrect. I mean that if you have random variable psi eta 1 and psi eta 2 and assume that distribution of eta 1 is absolute continuous with respect to distribution of eta 2, but sometimes it seems to me you may have even singularity. For example, assume that let me think. Distribution. So eta 1 and eta 2 are independent, uniformly distributed random variables, but eta 1 is psi, then psi, distribution of psi and psi eta 2 are singular. Maybe you have this result for special random variables, but this is not the general case. So the distribution of this is supported on the diagonal, and distribution of this is okay if you have uniform distribution is a square. So
I think that we discussed a case when H mu is some Ito processor, I think, yeah? H mu T.
So maybe yes. So we can consider H here as a integral with respect to mu of some function. So then it will satisfy.
Yeah, so the problem will be reduced to the filtration of Ito processes, yes?
Right, right.
So in general, it is not true. Yeah.
So when we
also have a question, maybe I missed something. So mu t is actually the push forward under xt, the solution of the original equation.
right.
And yt is a function of xt and some beta.
Come back. Yt
Yes.
in general just a function of measure.
Yes, but mu can be seen as a function of x.
And what?
I mean, it's very, like, it seems to be a very strange fact that they are independent. It's very non-trivial, seems to me.
If we consider just an integral, yes, you're right. So if we will write like mu s du, then we just have f of solution.
Yes, it's integral with respect to x.
Mu 0 du. So here, yes, this is eta process. So and the result is obvious. Also, if we consider like f from r d to r, and we will consider integral with respect to power of d, we will have the same like function of x from u1 s and so on, x u ds mu 0 d du. And here also we have the eta process. Okay.
Yes, I see. As you're saying, this looks non-trivial.
Yeah. Yeah. So for
The
this
whole statement.
Hmm?
The whole statement seems very untrivial. Non-trivial.
So here, when we consider, okay, for function h of the form when we have the let me write h of mu t, it will be just integral of some function, phi of u mu t du. Then here we will have the eta process and here. And the distribution will, so the Radon-Nikodym derivative will be equal just to this one, the same stochastic exponent. So now if I take the function psi, if I take a function psi, which is defined on the space of trajectories, these two, then I'm sorry, here is equal. Then the expectation with respect to probability measure p tilde rewritten just as expectation with this exponent. This is equal, and this is just will be the same when we replace y on beta. So if the initial h of mu was independent of beta, so then under our new probability measure, we will have here independence between h of mu and y. Okay, I recall that beta is independent on everything, so it's independent with respect to solution by assumption. Okay, so now when we will take the conditional expectation, it's we will use the following, that the independent, so-called the property of independence of future of the observable process. So if I denote by y the sigma algebra generated by all observable process, and if I take the some ft measurable random variable, then the conditional expectation and the probability measure tilde is equal. So we will have the following equality. How one can see this? If we consider the sigma algebra generated by increments, thank you. Then this the sigma algebra y will be just a sigma algebra generated by sigma algebra up to time t, and sigma algebra of increments after time t. And since we know that under probability p tilde y is a linear process, then y prime is independent of yt and independent of ft. So since this, we have the following equality, which gives us that this actually, when we will consider the to calculate the conditional expectation with respect to yt, actually we can consider the conditional expectation with bigger sigma algebra when we have here ft measurable random variable. So it will simplify our next calculations. Okay, so now just to say that P and P tilde, they are equivalent, and we can write the density of vice versa. And in this case, the inverse density we can write using the process y itself. So because on the probability space with measure p tilde, y itself is a Brownian motion. So here just we have the stochastic exponent of the usual form. Here y is linear process on this new space. And now in order to find our optimal filter to the initial problem, we will so this is it. We will use, so sometimes people call in literature it as a bias formula for conditional expectations. So we can change the measure or integral with respect to measure p by integral with respect to measure p tilde. So here we will consider the expectation with respect to p tilde. And now here this Sigma algebra generated by Wiener process in this new probability space. So here y is Brownian motion, and it is independent on process mu t, as we proved. And this process, which we have in denominator, we called unnormalized filter. So here we will first we will write the equation for this unnormalized filter of mu, which is given by this conditional expectation, and then to get the answer for initial problem, we will come back to it by using this representation. So let us state this theorem that we get. So if we have the functional, so recall here we have function h, which is a function that defined on the space of measures. So in the next theorem, I will state the result just for one case when h is the integral with respect to measure mu t, but it can be done for general case, but I didn't write it here because of more huge formulas, and like we need to use the derivative with respect to measures about which the previous times tell us Alexander. So, but it can be done for general case. So for the case when h of mu is just integral of some function phi with respect to measure mu, the normalized filter will satisfy the following stochastic differential equation. So here we have integral with respect dy. So now it is in our new probability space, it's a Wiener process, and the functionals L1 and L2 are defined as follows. So L1 just you can consider it as a generator of a like the action of generator of the initial stochastic differential equation with interaction on function phi. But here we have that the the coefficients depends on measure. So here what we write, so we have this coefficient and we integrate it with respect to mu again. So this is what we have. So in this formula, we have a normalized filter that acts on this measure, the function that depends on measure. This brackets denote that the integration with respect to measure with, of this function of u. Okay, the coefficient in stochastic part depends on the signal process. So here, as I said, for simplicity, for signal process, I take the function of measure, which is again integral with respect to measure. So this is we have from signal part, and h initial here h function of measure of this form. So this is how we can see that the dependence on observable process we get just in stochastic part here. Okay, the idea of the proof is quite standard. So we need to apply the eta formula for the function of process x, and things I consider, so my functional of measure is integral of phi. So applying eta formula and then integrating this equation, both part with respect to mu zero, actually, we can get the differential of integral of phi with respect to mu t. So here we just need to denote, I denote for base L tilde this part, and just a simple notation will give us what you saw in the statement. So this is a differential of function of measure, and now as you remember, for a normalized filter we need to find the conditional expectation of mt, so the stochastic exponent times function of measure. And recall that we have for this representation for stochastic exponent, we can write the by eta formula, we can write the product in such form. And now next step is to take the conditional expectation with respect to 1 sigma algebra. So I recall that on the previous step, we proved the result here that we do not need to take the conditional expectation with respect to yt, but if we have ft measurable process here, we will consider conditional expectation just with respect to 1 sigma algebra of all linear process. So this is important property why we do change of measure just to do this. So now in this equality we take the conditional expectation, and here the conditional expectation of integrals, how to deal with them. So actually the statement is the following. So if we have f and g are adapted processes, then we will have the following rules how we can put inside the integral the conditional expectation. So this here we have one conditional expectation, but here, as I recall, we can now change the y to yt, and we will have actually what we have in the statement of the theorem, because here actually we write the conditional expectation. Well, we can write it with respect to y s or y. So we have this statement. And also important that the integral with respect to w here disappears just because y and w are independent under p tilde. Okay, so this is the so-called analog of Zakai equation for unweighted filters, and in order to get the equation for initial optimal filter, we can define an innovation process as follows. So I recall the observable process has such form. So now if we define somehow we will shift to observable process by integral I'm sorry, we'll shifted it by optimal filter which we apply for f here. So the same f that we have here. And now such a process nu, which is defined by this differential equation or differential, we can prove that it is a Brownian motion under the with respect to sigma algebra generated by process y. So this is yt Brownian motion, but now it's under original probability measure. And again, the proof of this lemma is quite standard. We just need to prove that yt is, I'm sorry, here g is sigma algebra y. That nu t is a martingale, and to do this we just do this trick with add and subtract value at point s, and now this, and we split the integral from 0 to t, two parts, from s to from 0 to s and from s to t. And now we will consider this red part. We will prove that it is equal just to value nu at moment s, and indeed, so we just here maybe simple tricks with conditional expectations, and so we will get that this part just the innovation process at time s. And on the next step, we will check that this is 0, and it's also not hard to see. So this part red is 0. Again, it's just some tricks with conditional expectations. So nu t is a yt martingale, and to check that it's a Brownian motion, we calculate its quadratic variation, and it is equal to t because of the definition how we define it. So I'm sorry, here yt. So nu t is yt Brownian motion. And now when we have this, we can get so-called Gaussian-Stratonovich equation for optimal filter itself. So here, again, we have the same operators. I didn't write them here, but in L1 we have action of generator of initial stochastic differential equation, some sort, and L2 has the coefficient which depends on observable process itself. So here we underline here the dependence of observable process here, and it also appears here. And the proof also is maybe just repeating of ideas from known approaches. So what we need to apply eta formula for this fraction, as I recall. So we know the formulas for the chi equation for these parts. So this Vt is just numerator and denominator in these formulas, and then just applying eta formula here for this fraction. Well, it can be done here. So what we need to do just to collect together a part with dy, and after this replace process y by innovation process. So we know that innovation process is equal to y minus this integral. And after this, some here a lot of dt will disappears. So one will get this equation. So this is like analog of Cauchnir-Stratonovich equation that is known for usual stochastic differential equations, but here we applied it for measure valued, and I just want to recall that here I just write the formulas for this. Let me come back to the chi equation. So here I consider just a function of measure which is very simple and is just the integral with respect to measure mu. So we get this quite simple form of action of L tilde, or generator of the action of generator on this phi. But in general case, to deal with functions that depends on measures, we need to define, we need to use Lyon's derivatives of function h, and to just to find and write down this action of L tilde on function that depends on measure itself. So this is all for today, and this is just what we get for now.
Okay, thank you. And before we start some discussion, let me, since I am a participant of the project, let me make a comment. But to do this, Kateryna, can you for a moment stop sharing, and I will raise my whiteboard. Okay? No. So the idea was the following. Of course, we can.
Oh, we cannot hear you.
You are muted.
Oh, now it's okay.
Yes.
Yes.
Okay. Okay. So the idea was to find information about all measure-valued process mu t just using the integrals. Suppose that we have information about the integral with mu t for one fixed f0. And suppose that we want to know all mu t or to know even j mu t. I think that this problem is rather new because when we consider the picture of trajectories of our flow with interaction, then if we consider, for example, part of trajectories, then one can say that this is more or less the same statement, the same problem as we have seen in nonlinear filtering theory, because we have like a system of equation for all these trajectories, then fix some of these trajectories and want to know. But when we have the information about such integrals, suppose that function f0 is like this one, and then we have that different trajectories of our flow from time to time visit this region. So we have a much more complicated problem rather than in usual, at least in usual nonlinear filtration problems. This is the first what I wanted to say. Second one is that there exist some very interesting problems here, which also seems to be rather new. Suppose that we even have a very simple situation when we have not a flow with interaction. Suppose we have such an integral like 0t. Here is some function phi u v and w. Okay, another integral with respect to r. W dv dt ds. Yeah. Then we have Gaussian. This is a Gaussian process, and it is when we have here minus, for example, it is stationary. So I can write it like here, like this. Now assume that we have this situation, and that we have information about the integral over r. Here is f0 of u plus psi u du, and we want to know information about the integral of r j u plus psi u du. This seems to be nonlinear problem for this stationary Gaussian process psi, but it can be done linear. Let me show you. So let us introduce the local time LV of this process. So this is the integral of r delta v. Here is u plus psi u du. And you remember that we have usually the smoothness with respect to spatial variable. So psi is smooth stationary process, and this local time really exists because psi is centered, and at least one can try to take expectations there and easily see that it is finite. Yeah. Then using the local time, one can reformulate our problems. We have the information like this. We have the integral f0 lv dv, and we have the integral. We want to know the integral J V L V dV. And I claim that that is the problem which we already know. Why? It is not hard. It is rather technical problem to prove that this local time L is a random element. It's a random element in L2 are with some rapidly decreasing density. So, for example, with Gaussian density. Here, U square 2 du. Then, what is the problem? We have some vector f0 again from this Hilbert space. We have random element here. We know this scalar product f0l, and what we want to know another scalar product, this one. But to do this, it is natural to ask what is the distribution on the of L on this hyperplane. So we have like this one, and this is a set of phi's. This is a hyperplane, and we want to know what is a conditional distribution of this vector L in this space. But this it was proved by Skorokhod that this conditional distribution has good properties only in case when f0 is not arbitrary. When f0, at least he considered such case when f0 is admissive shift, yeah, for distribution of L for our local time. But for now, it seems to me that this is a very strange situation, and this local time has no admissive shifts. Why I'm thinking so? Because actually it is obtained from a Gaussian process, psi. A Gaussian process itself has admissive shift, and we know what it is. If we started with its white noise representation, so psi of u is like some integral from phi u minus v. Here is white noise w dv. Then the admissive shift for psi are like this. This is, let me find some other notation like this. For example, f of u is equal integral from r phi u minus v, and here is square integrate h v dv. These are all admissive shift for psi. Then we just have this f, and then we calculate a new one, delta v integral from r. Here is u plus psi u plus f u, and this is new random element which has it's a continuous distribution, but of course it is nonlinear transformation of the local time. So I think that we have to look on the case when f0 is just direction of differentiability of this of the measure of delta v, and here we have a new interesting problem. Which is generated by the filtration problem, which Kateryna presented to us in this talk. This is a first step which we now are doing. This was my comment, which I wanted to say. Okay, now I am stop sharing. Okay, so maybe somebody have another comments and questions, please.
So do I understand correct that you need to consider not equation with interaction with finitely many Brownian motions, but with Wiener sheet? Because you need
This is, of
a
course,
lot of.
this is our aim. Still, I think that even if we have a finite number of Wiener processes, we get a new problem related, as I said, to the reason that when we just fix the integral with respect to measure, for example, even suppose that we have much more simple situation, that we know the value of mu t from some fixed domain, yes, then you don't know information about the trajectories of the flow x, because they can visit for a moment, then go up, or if this is interval and so on. So this is new, I think. Since then,
So if
I
you have a
think
lot of noise, then you don't know.
yes, in this case, I don't know, and in this case, of course, this is our aim. We will do this. Yeah.
And what about uniqueness of the chi-type equation?
I think that is more or less evident, because all what we are all what we are doing, we get at least in which case which Katya presented, we have elliptic operators, like so we
For these simple equations with interaction.
yes, exactly. Of course, when we will have the equation with Lyon's derivative, it became to be a new question.
You see, when you have a traditional filter problem, you get SPD.
Yes.
But now you have measure valued process. So values of your process, so you consider process in infinite dimensional space.
Yes, exactly.
So you have to consider SPDs in infinite dimensional space.
It seems to, but in those simple cases which we have seen today, it's okay. But of course, when we will have a general case, as I said, with Lyon derivatives, it is unclear right now.
Because for usual SPDs, the reference measure is Lebesgue measure, and in infinite dimensional measure, you have to think.
This is what we are discussing with Alexander in his talk. He just briefly mentioned that we are looking for some good reference measure for equation with interaction. Yeah.
So probably you have to have Wiener sheet integral with respect to Wiener sheet, and the drift should be inside Cameron-Martin space.
Yes, exactly. We also the formulas which Katya shows today is only part what we get, and we discuss it, of course, this thing about the admissive shifts and so on. This formulation about local time seems to be interesting, and I think we'll get something interesting here.
Thanks.
Okay, other questions, please?
I still have a question about this independence result. I mean, if you use this theory from like the book of Lipser and Shiryaev, for it on the filtration of stochastic processes, you will get most likely only orthogonality of measures, but not necessarily independence.
Okay, as I said, this is just first attempt, so
I see. No, I see.
yeah.
Thank you.
Okay, some other questions, please? If no, then Kateryna, thank you again, and we will see continuation next semester. And Georgi, who is the next speaker?
Next seminar May 14, and the speaker is Andrea Tolini from Washington.
Okay, now do you know his subject?
Yes,
Or still no?
heating times in random graphs.
Oh, okay, good. Good. Okay, so see you then after 2 weeks.
Okay,
Bye.
see you. Goodbye.
Bye.